So as usual, we start with loading the also various packages. So we have all the different things here, and then what we do now is we load a diffraction pattern, and that is very similar to the one that we were using on Google Colab. What it will do is it will download this old one. I haven't changed. Okay, that's not the right one. Okay, I hope the new one is up on the it's a repository for that. We go to the on your own computer. If you downloaded the whole thing and updated that, then you should have an example data in day 2, and we by select main we activate that, and we can then look at that or not. That is funny. So this one does not look. Okay. So the same thing as before. You notice we have many more of these thickness fringes. So it was a significantly thicker sample, right? It was also at 200 kV. And if we plot it on a logarithmic scale, it's funny that this is not working. Maybe we should go. Doesn't like that one. Maybe I don't know what they did. So it works on this, but not on logarithmic scales. It is funny. I know why. Let's try to get rid of this. Nope. Okay. At least we should see whether it works on my. No, it doesn't show any of my plots here. Oh, okay. This one does. The key thing in a diffraction pattern is that we find our center, right? In the cases of a convergent beam pattern, that is relatively easy. So it's a zero disk, and it is the center of that disk. We can zoom in and make it very clear. For the moment, that is good enough. And so we read that center. And what we do now is we do the same thing as what we did in the beginning. We are just calculating the spot pattern. And with verbose, we see that we have quite a few of them. And we can change around field of view. We change just 0.1 is quite high. 0.05. So a thicker sample will have more of them. And then it looks more like what we saw before. So what we do next is we're trying, this is going to be quite quick here actually. If we would see something. Okay. We have to try that in Google Colab. There's no other way. And what I wanted you to do is to follow that. And I can't update it right now, so this is not good. Okay. I'm not sure why it's not coming up. No, this one works. This is an old version, so I cannot update my thing. Okay. So let's see how far we come with this one. And maybe I can update it from here. That does not work. Okay. Yeah, that's the problem. Something got backwards and forward and it doesn't stash my stuff. So let's work here. So it installs PyTemLab on Google Colab. And this, yeah, it's definitely the wrong version, so it did not update what I had. Oh, and it will not work, of course, right? Because we have changed the environment for matplotlib. So what we have to do is we have to restart the session and then do matplotlib with the widget so that we can change our contrast and stuff. This is definitely the old version. Yeah, that's the problem. So we have to get rid of all of, yeah, that is not good. Okay. So I can actually connect it to my Google Drive. But it also can download this file here from GitHub. And on this side here, I need to have my file. So it downloaded it directly in our directory. Here we are. So it took a while to get that. So it downloaded that here. We can conveniently do any of those. And so we can plot this pattern. And in Google Colab, it works. So we have a few things that we look for. As we said before, if we look at diffraction patterns, and we do that so that we are that we can follow better what we are doing in the next part. So we look at the symmetry of the center. And it's clearly fourfold, so it's the same thing as we had before, silicon 110, right? So it's cubic because the symmetry is square here. We look at the symmetry of the whole pattern that can actually be different, especially if you have small distortions. So the whole pattern is also, and you see on so we have color bar, and we can make it a bit brighter. And the whole pattern is also square. So square, square, square. All of that is okay. We can double check how exact we have set, how exactly we have set tilted. So we look at the opposite sides here and maybe a touch to the right and maybe a touch to the top. So very, very little of a deviation from the ideal points. And in the fringes in the center, as we said, that is an indication of, in this case, of the thickness fringes. So we have a relative thick area here. So we had with 80, we had about 2 fringes in the simulation. And here we have certainly many, many more. So we are talking about 250 nanometer or so. On a logarithmic scale, that is normally what we are trying to do because it equilibrates. And I need color bar, if you can do that too. So we want the dark ones dark. And then we can look at this larger thicknesses. Very nicely, you can see the changes, not of the symmetry, but of the feature frequency in the different orientations, right? So we see this spot part that we saw earlier, but the frequencies and in the different orientations are very, very different in this diffracted disk. What did we kind of wrong? Well, it could have been a little bit larger. So this one is not as wide as we had it in the other one. And as we said before, so the next thing is really finding the center. And in a mathematical point of view, if you have it halfway centered, the center should also be the center of mass in your image or in your diffraction pattern. We can do that a little bit nicer, possibly, and makes it as big as our pattern. So most of the times, the more accurate you do that, the better. So we have our center at this point. And we read it out. So in this case, so it's a 2024 by 2024. You see that should be 48. Should be 1024, and it is a little bit off. If you're on the microscope and you find your center on your camera, it is actually quite advantageous of doing that when you're on the microscope, because then everything is nicely centered, especially if you have a whole bunch of them, as you will see in the 4D STEM run. They always try to center that very accurately to not being bogged down with having to find the center. So the next thing is, okay, so here we have the same problem I had before. And I will update that in a moment, because I can do that from here. So crystal tools. And we need the tags experiment. And we want to make that tell us what we did wrong. No, that's a bit much. What we see get here, maybe not. Ah. I'm not sure what I named it. So it's a diffraction dictionary that we get back. And we want to tell us how many we have. And obviously, there is something wrong, because we see that we have some dynamically activated pattern, and we'll see that in a moment. So let's, oh no. Okay, that's that's not good. Okay, so programming together. So we have this pot here that was the same as we just did. I'm not sure why it did not update. So we do this. And we have our diffraction pattern. Obviously, we have a few too many here. Where is our problem? We have a very high excitation error. So if we do that a little bit more sensible, then we have just a few of them. If we go back here, maybe we get a few more. So the excitation error is, as we remember, so what are the different parts that we have here? So we have our maximum Miller indices, maximum Miller index. So we have all the indices from -15 to +15 in all three directions. So that are the ones we are doing. The wavelength is given by our acceleration voltage. So 1 over the wavelength is our wave vector. The position for that is our zone axis. So here we do 0, 0, 1. So we come straight down. And then we calculate that. And we got it. Any other one can be easily changed. So let's try one like 1, 1, 1. And the centerpiece, immediately you see, is a hexagon, right? So the inner parts here are a hexagon. So 6-fold. Should we go to another one? Let's put a 0 somewhere. And we see this is here 0, right? So this is now a rectangular pattern. There are some of them missing. And so they can be dynamically activated by having a double diffraction. So if you diffract in this direction and in this direction and in that direction, so first we diffract here, then we go to the diffraction in this direction, then we end up here, right? So we have an extra one that we can plot if we want to. This is not the right one. So this is just the that's not where I want to be either. Okay, so now we want to plot the experimental and the together. And we see that we have the center relative correct. Oh, we have still 1, 1, 0. That's not good, right? So we want to go into 1, 0 direction. That is our diffraction pattern. Okay. Obviously, our scale is completely off. We have it over here. And it should be much further in. Do we have the 200 kV? Yes, we had the 200 kV, right? 200,000 volts, okay. So what I want to do is to find the pixel size here. And so the exact calibration of this diffraction pattern. Wrong direction. So we can increase the pixel size here, reduce the real space distances. And we can get the exact rotation here. Rotation minus 10. Okay, now I don't remember in which direction it rotates, but I think this is counterclockwise. Okay, it's closer to 15. My positioning is still wrong. So it's closer to 45. Okay, that was a lucky guess. And if we do our convergence angle, that is a bit too big, obviously, but you can see that you can immediately mesh. What's a good guess? 0.7. So we're still not perfect in our diffraction parts here, right? But because we have all the different go back a little bit. So we have them now not only regrouped or assigned. So we have the different diffraction patterns here on indexed by just putting our different spots directly into the center. What we have more than that, we also have determined the exact convergence angle, because the disks, as we saw, are directly our measure for the convergence angle. And we did that now in 1/nanometer in the same orientation as we have our diffraction pattern. We got all the different diffraction spots. So there are no diffraction spots that are forbidden, and can be reached by a double diffraction of the different diffraction spots. If you put a little bit more time onto that, then you can make that very exact, right? Ideally, of course, you would want to do that by having something fine set. It's very difficult for normal methods to find these kind of circles. And the reason is relatively clear. So they have a lot of different structures in there. One way of analyzing these kind of structures is, of course, making them rotational invariant, because they all rotate around, and try to match them. The other one is to try to match them with simulation. The simulations that we had, it took a minute or two. So by the time you're at these large thicknesses, you have quite a problem to realize them. So the idea is always to minimize in this case, the simulations, and try to find as much out as you can so that you're approximately in the right order already. And so just finding the center of these disks is important. It cannot be done with the center of the mass. If we just look at this diffraction spot, the bottom part is much brighter than the top, so you will never find that. If you try to find that with a blob, that will also go with the center of the mass, and so it will always be at the wrong position. It's not a trivial task to find them. Our eyes are very, very nice, quick, and easy. So this is one of the times when a neural network can find it much, much faster. So like we found the atom positions, we can now, if we have them for different thicknesses, we can find this at center of the disk extremely fast and easy. I thought it would take a little bit longer, but one thing is clear: we have a very we have now actually not only indexed our diffraction pattern, but we have with that also calibrated our length scales here, because we know exactly how the diffraction pattern should be. The accuracy of that kind of pattern and change can be really tested out relatively easy. Let's say we make that by 10% different. And 10% is very, very clear. If you want to do something like that, would you look like I did that now? On the closest one? Of course not. So what you really want is one that you still see and has a relatively large angle. Okay, this one we don't see very nicely. So you want to have the largest angle that you can discriminate, and then you have this disk. There are different ways to do that otherwise, if you want to do it by hand, so that you get a bit. Okay, now let's go 5%. Is also very clear. So certainly within 1% easily. That's even too much, right? So you can do that actually with sub% precision. So that's a very precise way of doing that. So it's much easier if you have real blobs in there. So if you have parallel illumination, we have just spots. These spots can be found with a blob finder. Here we can't. Another way of determining the reciprocal space here would be, as we did it space implicitly here, we went from, okay, let's select two deflections here. So we went from the center to the center, and we know this G vector. So that's in principle what we did. If you want to do that with the line scans, and it's often easier to go through the center and measure from one end of the disk to the other, the one you can find easily. So from the center to the rim is always the same distance, right? We have circular disks, hopefully. And so different ways of calibrating these diffraction patterns. What you will see is that a lot of people for this 3D stem. So now we, for the stem, if we want to optimize it, it's often better to have smaller disks because the computer can find them easier. If you then send this data to, so you acquire that, now you have a lot of diffraction patterns. Let's say we just talked about it, a few terabytes in very little time. You want to reduce that. All you really want to know is where are my spots, right? So you can find that spots fast with machine learning tools that were trained on your diffraction patterns that we simulated at this point in time, or with a blob finder. Any of that would work. If you do it with more information like we have here, it's getting significantly more difficult. Okay, well, That's as far as I wanted to go. I had plans that you guys are doing it yourself, and I can try to update that now to Google Colab. Now, this is not what I want to do. Good morning. Okay, so you should have the updated notebook now. In a way, in a little bit. Invalid notebook. Okay, nice. Why is that? Oh, this is 2025. Yeah. Okay, that's the confusion we had here. No. Ah, that's my problem. Okay, that was the confusion. I guess I have the wrong year. I updated that notebook and then I put it in the wrong directory. Okay, that needs more work here. I'm sorry. Yeah, here we are in 2026. If I save that to 2000. That should work. And you can try that out on any other convergent beam pattern part. No, this is also invalid. Okay. Okay. It's a valid one here. So there is another level of, since we have some time, there's another level of information in your convergent beam pattern. And if we look at that carefully, we see a little bit of that. So there are actually lines through here. Where is my, didn't I have a Google Colab here? Okay. So I go to my drive. No. This is stuff. That is my. I think it's on OneDrive, not on Google Colab. Okay, so I can't do that right now. What I wanted to do. Okay. We can actually see the Holz line in this thing. So while we have time, I can go to MSE. We can go to the diffraction. Actually a notebook. And I'm not going through that, but in this case, this is actually from a book from micro diffraction of Spence and Sewell. So that is the silicon 211. And these very dominant lines in here are the so-called Holz lines. So they are the deficient lines from the high order Lowry zone ring, so from that reflections. And so these have usually very, very high Miller indices and are related to very high angles. If we do the simulation, we see the fat lines here are our Kikuchi lines. So we have two Kikuchi lines here. And in the center, we have a whole bunch of Holz lines. The diffraction pattern is also indicated here. You notice that the, how is this rotated? Anyway, you notice that in such a high index zone axis, the terms Laue zone does not really make a lot of sense anymore because they kind of are combining. The Holz lines, however, are still very dominant. And with the simple trigonometric functions, you can actually determine these Holz lines very accurately. And the accuracy here is actually better than this. Why is there something wrong? You see that these three Holz lines meet exactly in one point. In the image, however, there is a little triangle. So they don't meet exactly in one spot. And the question is, where does that come from? If you change that around and you change the lattice parameter by 1 picometer in one direction, the other, or in all three, it will move all of them. But what's really happening here is a small mistilt. You see the small mistilts that we have introduced. Okay, I have to go a little bit smaller here. So you see now the disk, the red circle is my incident beam disk. I shifted it a little, or did shift it in reciprocal space. That is correct, actually, because a shift in reciprocal space is a tilt. So if I move in reciprocal space, it is actually a tilt. So I tilted the beam, in that case, in my simulation, a little bit over. And now my triangle is a triangle. So how big of a tilt is that? Well, we can double check here in our thing. So the mistilt in alpha is 0.7 milliradian, and in the other one, 1 milliradian. So it is around 0.1 degrees, right? So extremely small, and you cannot try to do that with the stage anymore. Obviously, you have to do some beam tilt, and you can see that actually also in, it's too big, sorry, in the disk itself, you can see that the left-hand side has many more stripes here than on the right-hand side. So the distribution of the intensity is not perfect. Now, something like that can, of course, be calibrated with an automatic beam tilt by itself very easily. And then let's look at this other stuff. So there are many more lines in here that we see in the background. So these faint lines here. And if we increase the maximum HKL here, you see our sample is relatively thick, right? 0.1 over 0.02, so 200 nanometer. And then you have all these faint lines. and they also match extremely well. It's purely trigonometry. There is nothing done here, right? When you calculate the high angular, the Holtz ring, Holtz reflections, I calculate immediately also these Holtz lines. I calculate the Holtz lines in so-called half space. So what is that? I take from this center, a line is defined by the distance from the center and the angle. That is unambiguously defining a line. The direction of that vector to the nearest point of the line is directly correlated with our G vector, right? So I don't have to do anything else but adjust this distance, and the angle is 90 degrees to it. So I have all of those values already, and I don't need to do a lot of calculations. So all we really need to do is find our mesh of G vectors, see which ones are activated, and then we can do that. The deformation of that, how much did we at the time deform that? Yeah, here. 0.4 picometer, 0.004 angstrom. And things fall apart. So depending on your Young's modulus and how much stress is deforming your crystal, you can measure that down, in the case of silicon, to kilopascal deformation, and you can do that locally, and actually you get the full stress tensor out of that because you have to mesh all of them. So shear and all the other tetragonal distortion, all of those things can be put in, and it's sort of and measured. So the stress tensor, just for your to remind you, the stress tensor itself is really defined on the basis of the unit cell. So you have a cubic unit cell that is perfectly cube. Any kind of distortion of that cube is your stress, and the stress tensor is how that is deformed. Okay, so that is super sensitive method. So you can measure actually things like dopant would not work, but certainly alloying works. Amount of, if you have Vangout's law, right, a small amount of copper and aluminum will be detected on that system. And so if there is any, let's say there's some Cottrell cloud around a dislocation, you can actually see that. You can map the strain field of dislocations with that. All of that stuff is possible and directly accessible to you with this.